Why does a thrown ball always obey the same exact law of motion, every single time, without exception? And yet, why is a snowflake, forged from the same laws of physics, never the same twice? How can our universe be a place of both rigid, unbreakable rules, and a sprawling canvas of chaos, creativity, and infinite, surprising variety? Your heart beats in a reliable rhythm, yet the spiral of a galaxy is a unique cosmic fingerprint. The contradiction is everywhere. You'd think these two realities would be mortal enemies. Ironclad law versus unpredictable freedom. But what if they aren't? What if they are two sides of the same cosmic coin, locked in a delicate dance? What if I told you there's a single, beautiful principle that writes the unchangeable laws, and a single, dramatic twist on that principle that creates everything interesting, everything complex, everything from the form of a star and the structure of a galaxy, to the fact that you exist at all? To understand this dance, we have to pull back the curtain on the universe's most fundamental secret. It's a rule so deep it's not even a law of physics itself, it is the reason we have laws of physics in the first place. This grand idea is captured in a single, elegant word: symmetry. Now, your first thought is probably a butterfly's wings, or your own reflection in a mirror. That's a great start, it's called bilateral symmetry. But in physics, the concept explodes into something far more powerful, far more profound. In this context, a symmetry is any transformation you can make that leaves the situation fundamentally unchanged. It's the universe having a poker face. You can change your point of view, but the rules of the game don't even blink. Let's make this concrete. Imagine you're a scientist in a sealed, windowless laboratory, running a sensitive experiment on gravity. Now, what if, overnight, a secret organization put that entire lab on a giant, silent, perfectly smooth maglev train and moved it 1,000 miles to the west? When you woke up and reran your experiment, would you get a different result? Would gravity be slightly weaker, or would a dropped ball fall slightly sideways? Of course not. The laws of physics demonstrably don't care about your coordinates on a map. They don't have a favorite spot. This profound indifference to absolute location is a fundamental symmetry of space itself. It's called translational symmetry. Now let's spin the lab. We put it on a giant turntable and rotate it by 47 degrees. Again, nothing changes. The universe doesn't have a pre-written up direction. From the perspective of a distant star, our up is constantly changing as the Earth spins and orbits. The laws work regardless. That's rotational symmetry. Finally, what if you just waited? You pack up, go on a year-long vacation, come back, and do the exact same experiment again. The result would be identical. The fundamental constants of nature aren't different on Thursdays, or in 2024 versus 1066. That's time translation symmetry. This one is arguably the most important for life and science. It's the universe's promise that the rules that work yesterday will still work tomorrow. Without this, science itself would be a fool's errand. Every day would be a completely new reality with new rules. We could never learn, predict, or build anything. For decades, these symmetries were noted, but treated as obvious. Almost boringly self-evident. But in 1915, a brilliant German mathematician named Emmy Noether looked at these boring symmetries and saw something no one else had ever seen. She uncovered the secret contract. Working at a time when women were often barred from holding official academic positions, Noether produced one of the most beautiful and powerful theorems in all of science. Noether's theorem. In simple terms, it states that for every continuous symmetry you find in the laws of nature, there must be a corresponding quantity that is conserved. A number that cannot change, no matter what. An account the universe is forced to keep perfectly balanced. Suddenly, the universe wasn't just following rules, it was upholding a bargain. That translational symmetry, the law's indifference to being shifted left or right? Noether proved that this symmetry is the direct mathematical reason that linear momentum is conserved. The fact that a hockey puck gliding on frictionless ice will just keep gliding forever in a straight line isn't a coincidence. It is the universe paying its debt for space being the same everywhere. The universe's indifference to being rotated? That rotational symmetry? That is the sole reason that angular momentum is conserved. It's why a spinning ice skater can pull in her arms to spin faster, or why a gyroscope is so stubbornly stable. They are all, in their own way, performing a beautiful, swirling dance choreographed by a fundamental symmetry of space itself. And the universe not caring what time it is? That time translation symmetry? That is the origin of the most foundational law of all, the conservation of energy. Energy cannot be created or destroyed, precisely because the fundamental rules of the game don't change from moment to moment. This is absolutely staggering. Stop and think about this. The most solid, dependable laws we know, the conservation of energy, momentum, charge, they aren't arbitrary rules baked into the universe. They are the logical, unavoidable consequence of the universe's most basic symmetries. They are the universe keeping its promises. But this powerful realization immediately creates an enormous problem. If reality is built on this bedrock of perfect, unwavering symmetry, then why isn't the universe just a perfectly uniform, symmetrical, and featureless cosmic soup? Where does all the stuff, the structure, the pattern, the complexity, come from? The answer is that sometimes, the rulebook remains perfect, but reality itself commits a beautiful crime. It breaks the symmetry. This isn't like breaking a law of physics, which is impossible. This is something far more subtle and creative. It's a phenomenon called spontaneous symmetry breaking. And it is the engine that drives the creation of all complexity in the universe. Let's go back to our balanced pencil, perched perfectly on its sharpest point. The situation is a portrait of perfect symmetry. There's a full 360 degrees of directions in which it can fall, and the law of gravity has absolutely no preference for any of them. The laws governing the system are perfectly symmetric. But can the pencil remain there? No. That state is unstable. The slightest quantum vibration, a single stray air molecule, a cosmic ray from a distant supernova, the universe is filled with tiny, unavoidable nudges. The pencil must fall. And in that moment of falling, it has to choose one direction out of an infinity of equally valid possibilities. The final state, the pencil lying flat on the table, has shattered the initial symmetry. It points decisively in one specific direction, a direction that was in no way preordained by the laws of physics. The rules remain symmetric, the outcome did not. This principle is at work everywhere, hiding in plain sight. Think of water vapor, a gas. Its H2O molecules are flying around in complete chaos. No direction is special. The state is highly symmetric. But as you cool it down, energy is removed, and the molecules must find a lower energy state. They begin to lock into place, forming a crystal, a snowflake. Suddenly, a beautiful and complex structure emerges. It has specific axes, a stunning six-pointed pattern. The system has spontaneously chosen a particular orientation from an infinite number of possibilities. A tiny imperfection in one spot cascades outwards, setting the blueprint for the entire structure. The laws of electromagnetism that govern the water molecules are the same, perfectly symmetric laws. But the state of the system broke the symmetry and created an intricate pattern. Now, let's look at a magnet. Take a lump of iron. Above a specific temperature, known as the Curie temperature, it's just a dull, non-magnetic lump of metal. Why? Because the iron is composed of countless tiny magnetic regions called domains, and at high temperatures, these domains are all pointing in random directions, like a disorganized, shouting crowd. Their effects all cancel out. The overall system is symmetric, no net north, no net south. But now cool it down. As the thermal energy that was shaking them around dissipates, the domains begin to feel their neighbors. It becomes energetically favorable for them to align. They start to form a consensus. And then, at the Curie point, a phase transition occurs. The domains lock into a shared direction. They collectively choose which way is north. The fundamental equations of magnetism are still perfectly symmetrical, but the magnet itself is not. It has a specific directionality. It broke the symmetry, and in doing so, it acquired an entirely new, emergent property, a powerful, long-range magnetic field. The pencil, the snowflake, the magnet, they all peel back the curtain on the universe's secret creative process. The symmetric laws provide an infinite menu of possibilities, and then the system, forced by instability, chooses one dish. But this principle doesn't just make snowflakes and magnets. It makes you. It made every atom in your body. Because the entire universe, in its very first, fiery moments, made a similar choice. A choice that gave the cosmos its substance, its very texture. Now we must talk about the Higgs field. You've almost certainly heard it called the God particle, a name most physicists dislike. What it really is the agent of the most important symmetry-breaking event in cosmic history. You hear that it gives particles mass. But what does that actually mean? The answer is one of the most elegant stories in science, spontaneous symmetry breaking on a truly cosmic scale. Let's travel back in time. To the first picosecond after the Big Bang. The universe is an unimaginably hot, dense plasma, 1 billion times hotter than the core of our sun. At this searing temperature, the forces of nature that we know as separate entities, electromagnetism and the weak nuclear force, were merged into a single, unified electroweak force. All elementary particles were massless, zipping around at the speed of light. The equations governing this state were pristine, perfect, and utterly symmetrical. In this primordial state, the Higgs field existed, but it was in a symmetrical state, like our pencil balanced on its tip. Physicists visualize its potential energy as a shape famously called the Mexican hat potential. Imagine a grand, circular ballroom floor with a steep, perfectly round hill in the very center. At the extreme temperatures of the early universe, the Higgs field was balanced right on top of that central peak. A marble placed there could roll down in any of the 360 degrees of direction. All paths were equal. Perfect symmetry. But as the universe expanded, it cooled. Rapidly. As it crossed the critical temperature threshold, just 10 to the power of -12 seconds after the Big Bang, that central peak became an unstable place to be. The Higgs field had to fall. It was energetically forced to seek a lower energy state, to roll down off the hill and into the circular valley, the brim of the hat, that surrounded it. And just like the falling pencil, it had to choose a direction. It tumbled down and settled into one specific, arbitrary point in that vast, circular valley. At that precise instant, everything changed forever. The entire universe, from one end to the other, became filled with the potential energy of this Higgs field, now resting in its new, asymmetric, low-energy state. This background field is everywhere. It is a fundamental feature of the vacuum of space itself. You are wading through it right now. And here is the astonishing key: different elementary particles interact with this now active field in different ways. It's like a universal cosmic molasses. Some particles, like the photon, the particle of light, have no interaction with it whatsoever. They are immune to its effects. They slip through this field as if it wasn't there, continuing to travel at the speed of light, unimpeded. We say they are massless. But other particles have a very different experience. The quarks that build your protons and neutrons, the electrons that orbit your atoms, and especially the W and Z bosons that carry the weak nuclear force, they get snagged. They constantly bump into and interact with the Higgs field. This constant interaction, this drag or resistance to being accelerated through the Higgs field, is what we perceive as mass and its consequence, inertia. Let's go back to our ballroom. The Higgs field settling in its valley is like a huge crowd of royal courtiers filling the ballroom floor. A photon is like a servant who can slip through the crowd unnoticed. No one pays it any mind. It zips across the room at full speed. Massless. An electron is a minor noble. A few courtiers turn their heads, nod, and try to make small talk. It gets slowed down slightly, finding it harder to start and stop. It has a small mass. But then a W boson, the king, enters the room. The crowd instantly swarms him. He is mobbed from all sides. He can barely move an inch without immense effort. His resistance to motion, his inertia, is enormous. He is extremely massive. The mass of every fundamental particle, the very substance that gives reality its heft and structure, is not an inherent property of the particle itself. It is a measure of a relationship. It's the strength of its interaction with a cosmic field that only exists in its current form because it spontaneously broke a perfect symmetry at the dawn of time. Without this broken symmetry, there would be no atoms, no planets, no stars, no chemistry, no life. Just a thin, featureless soup of massless particles flying eternally apart at the speed of light. The beautiful Flaw is the author of all form. We see now the grand paradox. Perfect, symmetric laws provide the scaffolding of the universe, but the specific, messy, wonderful world we actually live in only exists because that pristine symmetry was shattered. This realization doesn't solve everything. In fact, it throws open the doors to some of the deepest, most unnerving mysteries at the very edge of modern physics. Ready to look at the cosmic crime scene? Once you possess the conceptual key, symmetry and its breaking, you start to see the universe as a series of clues to profound, unsolved crimes. Events that happened long ago but whose evidence is all around us. Case File 1. The Matter of Existence. Let's begin with the biggest mystery of all. Why are you here? Why does anything exist? According to our best theories, the Big Bang should have produced perfect, equal amounts of matter and its mirror image, antimatter. A fundamental symmetry known as CP symmetry, which states that the laws of physics should remain the same if you swap a particle for its antiparticle, charge conjugation, and also view its interactions in a mirror, parity inversion, should have kept the scales perfectly balanced. In the 1930s, physicist Paul Dirac's equations predicted antimatter before it was ever seen, a stunning intellectual achievement. And when we create matter in particle accelerators today, it always comes with an equal amount of antimatter. The problem is, when matter and antimatter meet, They annihilate each other in a spectacular flash of pure energy. So, if the early universe was perfectly symmetric, it should have been a cosmic cauldron of creation and immediate annihilation. The result? A vast, empty, boring universe filled with nothing but leftover photons. No galaxies, no planets, no people. Poof. Game over before it even began. But we are here. Our existence is the smoking gun. Observations show that for every billion pairs of matter and antimatter particles that annihilated, roughly one matter particle was left over. Our entire universe, every galaxy, every star, is built from that tiny, 1 in a billion sliver of cosmic leftovers. This proves that CP's symmetry must be broken. It's not a perfect symmetry. And indeed, experiments in the 1960s confirmed tiny violations of it in the decay of certain exotic particles. The problem is, the violations we've measured are nowhere near powerful enough to explain the sheer amount of matter we see. It's like finding a single, melted snowflake as evidence for a planet-covering blizzard. The clue is real, but it doesn't solve the case. Some bigger, unknown symmetry-breaking event must have happened to tip the scales so decisively. Case File 2, the too-perfect nucleus. Here's a weirder one. It's called the strong CP problem. The theory governing the strong nuclear force, the glue that holds protons and neutrons together in every atom, has a peculiar feature. Its equations naturally include a term, a kind of mathematical knob, that should cause massive violations of CP's symmetry inside the nucleus. Based on everything we know, this knob could be turned to any value, like a dial on a radio. If it were turned up even slightly, the neutron would have a different shape, and the consequences would be catastrophic for the structure of matter. Yet when we do experiments to measure the effect of this knob, we find it is turned down to 0, to an accuracy of 1 part in 10 billion. This is wildly unnatural. It's like finding a rifle that, by all rights, should have a massive, unpredictable recoil, but instead, it fires with perfect, unshakable stability every single time. It's too perfect. Why? This fine-tuning screams that we are missing something. Many physicists believe there must be a hidden symmetry we don't know about, one that protects the universe from this dangerous term. This led to the proposal of a new particle, the axion, whose existence would dynamically and automatically twist this knob back to 0, like a cosmic gyroscope that constantly stabilizes the rifle. If axions exist, they are also a leading candidate for the mysterious dark matter that holds our galaxies together. A puzzle born from a too-perfect symmetry might just solve the puzzle of our universe's missing mass. Case File 3, the broken arrow of time. Finally, there's the biggest symmetry break of all, one you experience every single second. Time. On the microscopic level, almost all the fundamental laws of physics don't care about the direction of time. They are time reversal symmetric. A video of 2 billiard balls colliding makes just as much physical sense if you play it backwards. But your life is not a reversible video. Coffee always cools, it never spontaneously heats up. Eggs scramble, they never unscramble. You remember the past, but you cannot remember the future. The arrow of time points stubbornly in only one direction, from past to future. Why this stark asymmetry in our macro world? The prevailing explanation is the second law of thermodynamics. It says that entropy, a measure of disorder, or the number of ways a system can be arranged, always increases in a closed system. An unshuffled deck of cards is an ordered, low-entropy state. There's only one way for it to be perfectly ordered. A shuffled deck is a disordered, high-entropy state. There are trillions upon trillions of ways for it to be shuffled. So when you randomize it, that's where it inevitably ends up. So, the arrow of time might just be the universe moving towards a more statistically probable state. But that just pushes the mystery one step back. It forces us to ask the real question: why was the universe in such a highly ordered, exquisitely low-entropy state at the Big Bang in the first place? Why did the cosmic deck start out perfectly unshuffled? That initial condition, that apparent choice of a special, and probable starting point, might be the single greatest symmetry break of all. The one that allows for cause and effect, for memory, for history, and for the entire magnificent unfolding story of the cosmos. So where does this leave us? We've journeyed from the mundane to the cosmic, from a falling pencil to the dawn of time. And we've found the same story, told over and over. The universe is written with 2 hands. One hand is symmetry. It is the stern legislator, the author of the universe's ironclad contracts, the permanent rules of the game. It is the source of all conservation laws, of predictability, of the very notion that reality is stable and understandable. Symmetry provides the perfect, infinite, empty stage. The other hand is symmetry breaking. It is the wild poet, the creative artist, the agent of all change. It is the source of all structure, all pattern, all identity, and all complexity. It takes the infinite menu of possibilities allowed by the symmetric laws and bravely chooses one. It is the source of form, of history, of the story of you. Symmetry breaking choreographs the dance. Law and freedom are not enemies. They are partners. Rigidity and creativity are not in conflict. They are two essential steps in the same cosmic process. Invariance sets the stage, and the breaking of that invariance tells the story. And perhaps, just perhaps, this gives us a powerful new lens through which to view ourselves. As humans, we crave fairness, justice, equality. These are all expressions of symmetry. We build our societies on these noble principles. And yet, what is a life, if not a series of broken symmetries? Every life is defined not by its infinite potential, but by its actual choices. The path taken, the skills learned, the love given. Every creative act, whether painting a canvas or writing a song, is a deliberate breaking of a pristine symmetry, the blank page, the silent room. Every decision you make, to change a habit, to start a new journey, to forgive someone, is a purposeful break from your past trajectory. You are breaking the symmetry of what could have been to courageously create the reality of what is. So the next time you look at the chaotic beauty of the clouds, the intricate design of a snowflake, or even your own reflection in the mirror, remember the grand, paradoxical dance that made it all possible. The unbreakable laws of symmetry provided the potential, but it was the beautiful, necessary, creative act of breaking that potential that gave rise to our reality. If untangling these deep cosmic knots is the kind of journey you love to be on, there's a video right here on screen that tackles another of the universe's great what-ifs. I think you'll enjoy it. Give it a click. And now I want to hear from you. What's a tiny broken symmetry in your own life? A routine you shattered, a spontaneous choice you made that went against the grain, that ended up leading to something incredible? I truly believe our best stories live in those moments. Let me know in the comments below. And if you want a daily dose of cosmic perspective that makes you rethink everything, make sure you subscribe to the Science Audit. Thank you for thinking with me today.